clarifying the discreteness of space-time from the discreteness of space is it's crucial and it's really helpful. But with the time we have left, I'd like to talk about some of the particularly neat features and consequences of causal set theory. And you just said that the Planck length isn't a Lorentz invariant conception. We talked about how volume, on the other hand, is invariant. But Lorentz invariance, or Lorentz symmetry, as it's also known, is quite important to causal sets. But the term hasn't come up before on the show, actually, at all. And this is more a conceptual and a terminological question. But could you maybe just briefly say specifically what it is? And this, I think, is the crucial portion, how it connects to causal set theory and phenomenology.
Good. So Lorentz invariance it's an approximate symmetry of general relativity. So it's not an exact symmetry. It's approximate in the following sense, that it says that, so in general relativity, if you were to consider a small laboratory, say on a rocket ship, and you do an experiment, any kind of experiment of any sort of physics at all. So it could be particle physics, it could involve details. I mean, you're not going to fit the whole of CERN onto a small rocket ship, but something involving, radioactivity or anything involving gravity, falling things, or anything. So the idea is that any kind of physics, and you do that, and the experiment takes a certain amount of time that's not too long, right? Then you cannot tell whether or not that rocket ship is in motion. That's the or uniform motion, let's say. So of course you can tell if you look out the windows of the rocket ship, but that's against the rules of the game. You're not allowed. So in relativity, you're not allowed to look out of the windows of the rocket ship. But you can't tell. The physics just looks the same. The predictions that you make are using the same physics, and it's the same rules the same physics that you would use in special relativity, when there's no gravity. So that it's an approximate symmetry because it's not true for if the rocket ship's very large or the experiment lasts for a long time. Then you can tell that you're not that there's a non-uniform gravitational field, for example. So the physics is then different from the physics in special relativity. So it's an approximate symmetry, only applies for small labs for a short length of time, but we have no evidence that symmetry is broken. There's no evidence that there's a preferred frame in our space-time, and there's plenty of so the experimental bounds on the amount of violation of Lorentz invariance that is possible get smaller and smaller as we do more and more experiments.
Great. And another thing that I wanted to make sure that we got to was at the beginning of our conversation, when we were talking about Einstein-Rosen and ridges, EPR came up. And in the context of EPR, we were talking about non-locality and wormholes. But non-locality is one of the more unintuitive findings in quantum mechanics. And as we already said, it was something that Einstein protested vehemently. And am I right that causal sets side with QM on the matter rather than Einstein, and that they're resolutely non-local?
Right. So the non-locality that Einstein that perturbed him, I think, is something we might want to call acausality, where this spooky action at a distance that you referred to is action at a distance in space, so that something over here can instantaneously, something that happens over here can instantaneously affect something that happens over here in space. So and that's superluminal, because this shouldn't be able to affect this, because there's no time for light to have traveled from here to here. So that's the sort of non-locality that Einstein seemed to be perturbed about. And I think he had in mind the idea that the wave function was a real thing, and that if you consider the wave function to be a real thing, then indeed, if you do stuff over here, then it changes the wave function over there. So that was what he was bothered by, or didn't like at all. I think we would call that acausality, because it's propagation outside the future light cone. So it's not causal. It's not relativistically causal. You've got yeah. So causal sets are resolutely non-local, but they're also causal. So it's non-local but causal, which is different. So the non-locality of causal sets is non-local in time. So something that happens here can influence something that happens in its future, still in the causal future, but at a great distance, so to speak, in time, or in space-time, at a great distance in space-time, where distance, you see that it's a slippery term. So it's non-local in the sense that it jumps over it can jump over some region of space-time. But distance it's slippery, because the time, the proper time, the physical time between the two space-time atoms is actually really small. That's this peculiar thing about Lorentzian geometry. So the trajectory of a photon in space-time is a line. I'm now talking about the continuum, so nothing to do with causal sets at the moment. So the trajectory of a photon that travels at the speed of light is a line in space-time, and along that line, there is zero distance between any of the points on that line. So that's this astonishing, amazing, fall-off-your-chair feature of the geometry, Lorentzian geometry. There are these special directions, the null directions, or the light-like directions, in which there is no distance between the points in those directions. So when we see a photon that was produced at the surface of last scattering, it is as fresh. It took no time at all along its trajectory to reach us.
That captures the idea that time doesn't pass for photons.
Right. That phrase is referring to that mathematical fact that there's no. And then if you think about something that travels on a world line in space-time that's very, very, very close to that to that light-like null trajectory, to the photon trajectory, just it's not light-like, but very close to it, then you could, in some sense, the two events connected by that line are very far apart from each other, but they're also only one unit of Planck time away from each other. So that you have to rejig your concept of distance in a Lorentzian space-time, and causal sets capture that. So there are nearest neighbor space-time atoms with nothing, no space-time atoms between them. So they're nearest neighbors. But one can be at the beginning of the universe just after the Big Bang, and one can be here and now. And they're very it's a non-local connection across space-time, but it's completely causal. So there's no jumping outside the light cone.
No, that makes complete sense. I mean, they're next to each other. I mean, it's confusing, but it makes sense. Yes. I mean, when you take into account this notion of time not passing for a photon, that's what puts the ideas together for me. So one other dimension of causal set theory that I wanted to make sure we touched on, particularly because it was so surprising to me, was the connection to consciousness. Because aside from Penrose's writings on quantum nanotubules, I hadn't seen that much from serious physicists about the problem. So the hard problem of consciousness, for our listeners who aren't familiar with it or haven't heard episodes of the show that connect to it, can be contrasted with the easy problem of consciousness, which is sort of understanding maybe how the brain, what's going on in the brain that gives rise to experience. But the hard problem of consciousness is understanding just how something physical that doesn't seem like it should be the subject of qualitative feelings, like how this block of matter that is my brain has feelings and experiences of the world. How are we supposed to explain that? And what I understand is that causal set theory may have something to say about this.
That's what I am proposing. I can't say that any of my colleagues working on causal sets endorse what I am now going to say. So it's not something there's a consensus on at all in the community of workers on causal sets. So it's just something that I've proposed, and I'm happy to get feedback on. But the idea is that there are two types of thing in the world. So I hesitate to call it a dualism because of the baggage that comes along with that term. So it's not like that, but there are two types of thing, that they're intimately connected, right? So, and the two types of thing are the atoms of space-time that every space-time is made of, and the coming into being of those atoms of space-time, or the becoming of them, or the birth of them. And the idea is that the dynamics of causal sets is a process of the coming into being of the space-time atoms, and that process is a crucial part of, and is just as much a part of, and just as physical as the space-time atoms themselves. So, but they're obviously a different type of thing. So I sometimes use the slogan, the birth of a baby is not a baby. So the birth of a space-time atom, its coming into being, is not a space-time atom. They're different. They're just different types of thing, but they're intimately connected, because without the birth, there is no space-time atom. So, and the space-time atom is what's being born in the process. So the process is the birth. So people sometimes say how, and the idea is that it's the process that correlates with conscious experience. That's it. It's not the space-time atoms. It's not any particular thing. It's not any particular substance. It's not any particular event that corresponds with the actual having of the experience. It's the process. So the seat of consciousness is this process. And then so I've written a paper on it, and in the paper I strengthen this proposal by making connections between qualities of conscious experience and properties of the birth process in causal set theory, and say that you can, there are matches that you can make between the two things. So if you say, how does conscious experience, how does it interact with matter? That's like saying, how does the birth of a baby interact with a baby? It does. Interaction is the wrong term. It's
yeah. So the seed of consciousness, as you put it, it's the process of the birth of space-time atoms, or is the birth of space-time atoms just the root of the experience of the passage of time? Or is it both of these things?
It's difficult to say because people mean different things. These people have thought about these things for much longer than me. Probably you, since you have a philosophical background and training, but they mean things, and I don't know what people mean by them. But I think the quality. Somehow it's the quality of conscious experience that that the hard problem pertains to. The fact that it's live and inexorable and somehow uncommunicable. You can't experience what I'm experiencing, and I can't experience what you're experiencing. So, and the proposal is that it's our experience of the passage of time, which is what the hard problem is to do with. It's that aspect of our consciousness which is hard. That's
maybe what I should drill into then is the relationship of causal sets to the passage of time, and how does it. So this moving spotlight, I guess, is sort of the metaphor or the image that often comes up in discussions of the passage of time when we're wondering what distinguishes the present from the past and the future, especially if the past and the future, and this is kind of vague, are equally real. It's this spotlight that's tracking each successive moment. Something is in the now when it's in the spotlight. And the question that I have is, why? So does general relativity not leave room for this spotlight, but causal sets do? There's sort of a mechanism for the spotlight. That's one of the things that distinguishes the two theories.
Yes, in a sense that the process is the spotlight, but the process is this birth. So in the spotlight, one has the way it's described, the way I read it is that the whole space-time, the whole block already exists, and it's just that certain bits are illuminated. But the whole thing is there, right? Past, present, and future. Whereas in the causal set process, the birth process, fits more, but not quite. It fits more with the idea of a growing block. That the past is real, but the future doesn't, is open. And the present is the process. I tried that metaphor out in a paper, and the reviewer really didn't like it, so I took it out. But I can try it out on you.
A growing space-time worm.
The present is the process, but the thing about the causal set process is that you cannot view it from the outside in an objective way because it's partially ordered. So this is something which I've tried to express to various audiences. So let me try it here. So these space-time atoms are partially ordered. So you might have the set of space-time atoms that comprises an event, like it could be a neural event, some event that takes place in the brain. It takes 10 nanoseconds or some time, and it's the neuron is maybe a few millimeters long or something. Anyway, so it has some space-time volume in your brain, let's say, and it's made of space-time atoms. And those space-time atoms, they're partially ordered, not totally ordered. So some of the space-time atoms have no order relation between them. There's no fact of the matter about whether A happens before B or B happens before A. They just don't happen in any order. But if you try to put yourself outside the physics and look at it from the outside, so sort of run a movie of it in your brain, just imagine the space-time atoms being born, then you automatically, in your mind, put on that process a total order. You will have to imagine either atom A coming into being before B or B coming into being before A. That you can't imagine the process, this birth process, in a partial order. So there's no way to have an external view of this growing block process. The only way you can have a view of it, and this is my argument, is from within. If you're part of the physics, you can have a view of the process that's objective, and that is conscious experience. So your conscious experience is an internal view, internal objective view of this partially ordered process of the birth of space-time atoms. It's not something you can view from the outside. And that's something which I use to connect aspects of the debate about the hard problem with this proposal. That's, for me, that unlocks, or it illuminates the argument from knowledge, for example. That's for me.
When you say that the future isn't, so in your picture, it's this growing, I'll just use my words, it's this growing space-time worm or this growing block. You say that the future isn't real. And that makes sense to me because the space-time atoms that will eventually comprise the future, they haven't been born yet, so they're not real. I understand why the present is real because we're in it, and the space-time atoms are born in each now. I want to better understand why you still take the past to be real, and this is maybe it's not. It's a very used story, but you can't kick the past. I can't kick Julius Caesar many years ago. The way that I can pet my cat or something that's real right now. And I'm wondering if this maybe brings us back to non-locality, and maybe the reason that these space-time atoms in the past are still real is that they're still having non-local interactions with the present. With
yes,
the now.
Exactly. That's exactly the reason why they're still there. Because, yes, you can't kick Julius Caesar, but Julius Caesar can still perhaps not kick you, but kick something that hasn't happened yet, but in the future that's one Planck unit of proper time away from him.
Right. Through the photons that reflected off of it.
Okay. Right. The potential for causal efficacy, or what words to use, but yeah, they still have potency. They're still They're still able to have causal effects, no matter how far back in the past they are, because of the non-locality. Exactly. Yes, exactly right.